Okay, so good afternoon, everyone, and thank you to the organizers for organizing this very interesting workshop that I unfortunately don't have much time to participate in this week. And also thank you to everybody who's here just attending these talks and discussing. So I'm about to give some prospective views on galactic molecular studies. As Anael, this is not going to be an exhaustive overview because of time, because of the expertise that might be the areas that might be out of my expertise. So before I go on, I will just mention that this is a presentation prepared by both Cecilia Ceccarelli and myself, and that it is also based on several discussions we've had with many people. So let's go on. It makes sense to start this presentation with this nice figure that I took from the review by Brett McGuire, a very recent review, and which shows the evolution over the past 5 decades of the cumulative number of detected molecules in space, as different instrumentation and facilities in the sub-millimeter to centimeter wavelength range have been entering into play. This number has been steadily increasing, and it has basically exploded in the last year. This is thanks to mostly thanks to a very deep spectral survey that Cernicharo's group has done with the Yebes 40-meter telescope, and which has yielded more than 10, about 10, 15 or more new molecules in space. So even though the review by McGuire was accepted in June, I think this year, and they quote about 241 molecules detected, the real number today, so 3 or 4 months after, is about 250 or more. So this keeps evolving, and it makes a really rich molecular budget in a medium, the interstellar medium, which is expected to have a very inefficient molecular chemistry compared to the Earth, for example. So why do we search for all these molecules? Like what do we do with all these molecules? Why are they useful? So this is very briefly summarized in this slide. Basically, molecular lines are powerful diagnostic tools to derive the physical structure in terms of density, temperature, the kinematics, and also the chemical composition of whichever object we are studying. And in particular, the chemical composition is in itself a powerful tool to investigate the past history of the object under study. And if we have proper theories that make appropriate predictions, possibly the future of that object. So all in all, like molecular lines are pretty indispensable tools to get a pretty decent or rather complete picture of the targeted object. Fortunately, we are currently living in a quite lucky period in terms of observational facilities. We could say that we are like spoiled kids even, because we have all these powerful telescopes that have been, some of them working for decades, such as the IRAM 30-meter telescope, and other facilities that have been developed in the past decade or so, such as Herschel, ALMA, and NOEMA as a successor of the Plateau interferometer. So already today, we are able to do a lot of stuff and new stuff with what we have in hand. But if we are to ask how do we improve, where do we go from here, I will just throw it right away here. Like the molecular astronomer's wish list contains a couple items which are, well, I would say maybe obvious, like going for higher spatial resolution, high sensitivity. Also, the spectral capabilities are very important, obviously, for molecular studies. And there's a fourth item that I would like to develop more in the second part of the talk, which is a drift that we are having towards lower frequencies in these kind of studies. So we're going to see some examples. And before we do that, just a disclaimer that, of course, what follows is not exhaustive because there's not enough time. And we've concentrated only on a few examples that may illustrate some questions, some challenges for the future and why what we need in terms of observations to go forward. In particular, we're going to take the typical evolutionary sequence of a formation of low mass star, like the sun, and from the prestellar core up to the main sequence, and we will focus on the early stages of the formation of a star, in particular the prestellar core phase, which is this cold, also dense phase, which is characterized by a lot of condensation of molecules onto the icy mantles of dust grains. And also we will talk a lot about the protostellar phase, in terms of chemistry, of course, which has a lot more going on in terms of events. There's forming disks, the outflows, the infall onto the disk, onto the protostar. There is sublimation of molecules onto the gas phase, further chemistry in the hot gas phase, etc., etc. So in these two phases, from the list I was presenting before, basically everything is important for the two phases. Maybe the high angular resolution is not so critical for the prestellar core objects, but definitely for the protostellar phase, all of them are important, as we will see. And we're going to start with a high angular resolution, which is maybe the least complicated to present. And for that, we will focus on compact objects, of course, which are called hot corinos, which I'm sure you've heard a lot about, either here or elsewhere. This is a figure that Mathilde Bouvier kindly lent me, and she already talked about this yesterday. So hot corinos are basically compact areas of, typically, I would say mostly smaller than 100 AU, around the central protostar, which are hot and dense. And they are basically the areas where the icy mantles of dust grains have been sublimated into the gas phase. And therefore, all the molecules are released into the gas phase, and they undergo further reactions. And there's a whole lot of complex chemistry going on in these areas that we can capture with millimeter and submillimeter facilities. These enrichment, these molecules are usually known as ICOMs, interstellar complex organic molecules. And you can see from the millimeter spectra of hot corinos that they are very line rich. This is an example that was taken in the context of the NOEMA large program SOLIS. And this is already with a WIDEX, still with a WIDEX correlator, so not yet with a current polyfix correlator. You can see there's a wild amount of lines. So there's loads of ICOMs, and these lines are concentrated morphologically in very compact areas, as I already mentioned. And traditionally up to now, with typical like resolutions of 1 arc second, even 0.5 arc seconds, these are seen as blobs, like, or unresolved balls that emit in all these molecules. This slide shows a few examples of different hot corino sources in different molecular species, and you can see all these sources show roundish morphology. So this, because we cannot say much more, one can assume that all the different molecules are in the same area within this ball. But actually, if we go to higher resolutions, which is something we are starting to do in part of the world, mostly thanks to ALMA, we can see that the balls become something else. So this is an example of H212 protostar in Orion, in which there is a protostellar disk, which is seen almost edge on. And you can see in orange in the bottom panel and in black contours in the top panels, and different molecules that are overlaid in contours on top of these maps. You can see that, well, to begin with, nothing is round anymore. There's emission on top and on the bottom. So in the middle, we either have a heavy dust extinction or freeze out of molecules onto the grains. So we see molecules, icons mostly on top and on the bottom of this disk. And the emission from one molecule to the other is actually different. If you take the formamide case here, the emission is a little bit more compact and more towards the center in Z, in altitude, with respect to methanol, for example. So this is something that is in progress and we are still discussing, but it is something that can be telling us about the actual mechanism that triggers all this hot chemistry in the gas phase in terms of physics. So is it thermal evaporation from the central protostars, or is it more of a shocked region from the infalling material, or is it a bit of both? So resolving all these molecular structures can help us answer part of these questions, and also the kinematics, of course, of these molecules can help us unveil some of these questions. A different set of, just to mention that to reach this kind of observations, we need to go well below 0.1 arc seconds. Otherwise, we still see those balls we were seeing previously. So another big question is how these icons in hot corinos are formed. And for that, of course, angular resolution in hot corinos is appreciated, but we think that sensitivity is the big player here. Before going into this, just mention that there are two main paradigms, two main paths to form icons. One is the grain chemistry. Okay. One is the formation on the mantles of icy grains and further evaporation onto the gas phase. And the other one is evaporation of precursors that were in the mantle and further reactions to form these icons on the gas phase, in the gas phase, sorry. I exchanged the two. Actually, this is the grain one and this is the gas one. So it's basically gas versus grain. So why do I say that this is a sensitivity challenge? Is because we have recently found out that a very powerful tool to investigate how these icons are formed is by observing their deuterated forms, specifically by measuring the deuterium fraction of these icons, which means the fraction of a deuterated icon with respect to the abundance of the main isotope homologue of the icon. Now, I'll shortly say why, but just to mention that these are very challenging observationally. You can have here an example from PILS, the ALMA survey of IRAS 16293, in which, the authors kind of see deuterated glycolaldehyde among the forest of lines, which is not obvious. So the measurements of deuterium fraction of icons beyond methanol is relatively recent. And they actually reduced to one object. Why measuring this deuterium fraction is important is because, this here is where theory comes into place, and where I would like to make a small parenthesis to say that it is crucial to let's say, to be allies with theoretical chemists that tell us what can work and what cannot work in the interstellar medium in terms of chemical reactions, because not everything in the network works. And here, for example, we have the case of glycolaldehyde, also of ethanol, in which Bazard and collaborators calculated the efficiency, the energies involved in all the intermediate reactions in the gas phase leading to glycolaldehyde and to ethanol, and they made predictions on the deuterium fraction that should be measured in these objects for gas phase to be the main route of formation of glycolaldehyde. So If we have this prediction and the same kind of prediction on the grain, and then we can do these observations and measure the deuterium fraction and compare, and then just simply say, okay, this favors more gas phase or this favors more grain chemistry. However, as I already mentioned, measuring the deuterated forms of icons is everything but easy. It requires very high sensitivity, and because of the line crowding of the spectra, it also requires a good radiative transfer modeling. So far, as I mentioned, there's only one hot Corino system where the diffraction has been measured, and it's IRA 16293. So there's a lot more to be done if we want to progress in this area. So in summary, for the hot Corino chapter, I would say that, well, just first, don't assume that every protostar has a hot Corino. This is the main message. As of today, there's only about 20 protostars with well-established hot Corinos. There's even fewer protostars where the hot Corinos have been characterized in details in terms of icons, and there's just one hot Corino characterized in terms of deuterated icons. So the bottom line is the observational study of hot Corinos is a challenge from a sensitivity point of view, also from an angular resolution point of view, but especially from a sensitivity point of view. So it is very time consuming, and just to give an idea that we have needed a full large program with ALMA, which is FAUST, to characterize chemically and in a non-complete way 13 protostars. So it is really time consuming as of today. So definitely more sensitive interferometers would change this picture and improve the statistics. Okay, sorry. So I just want to dig into the second part of the talk by saying that not everything is about sensitivity and angular resolution. Obviously, we're talking about molecular studies, so the spectral capabilities are also very crucial. As you have seen, the spectra can be really crowded. So when we study a lot of molecules, we want to have a good spectral coverage in order to detect as many transitions as possible. And that's going to characterize the molecule as better as possible, and also the physical properties of the gas emitting that molecule. We also want high spectral resolution because kinematics can also be important, but also because we want to minimize the blending effect of the lines. That is not always possible even with high spectral resolution, but it is better. So I was glad to hear that instrumentation is developing in the right direction in this sense, with wider spectral coverage and spectral resolution. So in this sense, we are happy. And I would like now just to focus on the lower millimeter frequency topic, which is something that has been ringing us a little bit recently in our team, and also a little bit beyond our team. And I'll try to explain why we are drifting towards lower frequencies and why these can be complementary or even necessary to go forward. If we take the hot Corinos again, in the millimeter and sub-millimeter wavelength range, we have seen that the spectra are really crowded. There's two examples here on the left, one hot Corino in Orion at 1 millimeter, another one, the area 16293. These are really, really line crowded. In other words, they are line rich, especially in the 200 to 350 gigahertz range. The drawback, and it's becoming, every time it's becoming more of a drawback, is that there's so many line blends in these frequency ranges. There's also a lot of molecules for which most of the transitions, or many of them, are optically thick. And that hinders maybe a more accurate radiative transfer analysis. And also it has recently been found that for some cases, the dust, well, at least for some cases, the dust may be optically thick at these frequencies and obscure either completely or partially the embedded hot corino. And for this last part, I will point you to Marta's talk tomorrow, so I will not spoil anything else. Here are some predictions that Cecilia kindly provided for several ICOMs in the 50 to 300 gigahertz for a hot corino-like source. So it's hot compact region. And you can see why people have been targeting this frequency range. And that this other frequency range is a little bit harder to get to because of sensitivity. However, at these frequencies, line blends are less frequent. The lines are typically optically thinner, and the dust surrounding the embedded object is optically thinner also. So we have been starting to explore, or trying to explore this frequency range a little bit more lately to try to get more answers. However, as I mentioned, yeah, the sensitivity challenge at the required angular resolution is intensified if we go to lower frequencies in hot corinos. But hey, it is one of the directions to take. And I would like to point out that there are other types of objects and cases that are much less affected by this challenge. And this brings me to the topic of protostellar chemical diversity, and in particular, the story of carbon chains. So as Matilde already mentioned yesterday, not all protostars have hot corinos. Actually, there is a well-established and well-known chemical diversity among protostars. And the two extreme objects in this spectrum are hot corinos and WCCC objects. So hot corinos, I already mentioned that they are rich in ICOMs. They are compact and they are hot. On the other hand, WCCC objects are very deficient or completely or very deficient in ICOMs in the inner hot area. And they are, on the other hand, surrounded by a more extended envelope, which is rich in the so-called family of carbon chains, such as CCH, C4H, C3H2, but also C5,6H, cyanopolyenes, etc. And the difference in abundances between a WCCC in carbon chains and a hot corino can go up to 2 orders of magnitude. So it's something to be studying and understanding better. It is already believed that a different composition of the ice mantles during the cold phase is at the origin of this diversity, with more CO and methanol in the grains giving rise to hot corinos, whereas more methane on the grain mantles would give rise to a WCCC object after. But it is still a little bit unclear what causes this different mantle composition. And this is largely due to the poor statistics. So there's only, I think, about three WCCC objects known. And then in between, there's a few hybrid objects also. And what I would like to mention here is that there's also maybe a subjective bias towards studying ICOMs and not so much carbon chains. We believe that having a complete picture of the protostellar chemical diversity calls for a study of the two families of molecules. Also, just to point out, because of the angular resolution, that because the sublimation temperature of methane is 25 K, as opposed to 100 K for hot corinos, the area of the carbon chain emitting region is quite extended, about 2000 AU. And so we are not like a sub-arc second resolution in general is not a crucial requirement in this case. Now, here in the maps that I took from Matilde, thank you. These are ALMA maps in CCH of 3 Orion areas, protostellar areas. You can see that this CCH emission is pretty extended indeed, a few arc seconds. So again, angular resolution is not so much of a challenge. What is interesting to note is that carbon chains in general are emit most intensely in around the 3 millimeter range and also the 7 millimeter range. So here are some predictions for a typical temperature of WCCC 25K. I forgot to mention before that you should forget about the absolute scale here. This is just a not approximate. You should focus more on the shape of the line SED. And if we go to even heavier molecules, we see that the peak is displaced completely towards the lower frequencies. So the heavier the molecule in general, the lower the frequency you need to trace it. So as a summary here, the carbon chains in protostellar regions are better traced or best traced at the 3 to 7, 8, 10 millimeter range. It is ideal to have a broad spectral coverage because many of them are linear. So you have them equally spaced. So the broader you can observe spectrally, the more transitions you will get in there. Ideally, if we can have a dual band, that would be a jackpot. And as I mentioned, subarc second resolution is a priori not needed in this case. For prestellar cores, so this is a different kind of object. We are stepping back in the evolutionary sequence. We are talking about very cold and dense objects from which future protostars will be formed. Here, the temperature is much lower than for the WCCC objects. So even for the ICOMs, if we are to search for ICOMs in prestellar cores, we will be favoring the 2 to 3 millimeter range. Of course, if we go for carbon chains, we totally have to go longer than 3 millimeters. So yeah, as I mentioned, again, broad spectral coverage is optimal. We don't need subarc second resolution because these are also relatively extended sources. So if, I will refer to Eleonora's talk for carbon chains in this case. Just a note that the carbon chain family of molecules, especially if the object is cold, but not only, is best studied at the low frequency range of the millimeter domain, and that it is a relatively unexplored area of astrochemistry, in at least for protostellar objects. So I was just meaning to make a comparison of, not a comparison, just a brushing, but without going a lot into detail of different observatories to see if we can take this path of the carbon chain studies. The JVLA offers this 30 to 50, well, actually lower frequency range. There's currently no option to cover also the 100 gigahertz band. So currently, like a comprehensive study of carbon chains for one object maybe would need to ask on the one hand VLA and on the other hand somewhere else like ALMA and NOEMA. These are high frequencies for the VLA, so there's a small fraction of time suitable for these frequencies and only at nighttime. The spectral capabilities are pretty fair, but not as optimal as for NOEMA in terms of optimization between broad coverage and spectral resolution. And well, VLA is best suited for, is well suited for subarc second resolution cases at these frequencies, like for hot Corino studies. For ALMA, the band 135 to 50 gigahertz is planned. It should be expected in about 2 years, and I'm very excited about it. Again, the spectral capabilities as of today are good, not as optimal as for NOEMA. Just as a reference, the PIL survey of IRA 16293 with ALMA took, if I remember correctly, 18 frequency setups to cover 34 gigahertz at 244 kilohertz spectral resolution. So I believe something like that can be done with NOEMA in 2-3 tunings. It's best suited for subarc second resolution cases like hot Corinos. On the other hand, we have NOEMA, in which, well, we don't have these frequencies as of today. They are not planned either as of today. And well, it's sort of a pity. Of course, I heard Carl Schuster this morning saying that it is a technical there's a technical issue to implement this. But of course, we are here to dream. So in a world where the receiver cabin is infinite, I would really appreciate NOEMA having receivers that cover these frequencies. They would be, I believe, good fillers with the spectral capabilities. It would be optimal to target the objects I was mentioning in the previous couple slides, like WCCC objects and prestellar cores, also because they would require arc-second resolution or even worse, nothing more. So I believe it would be nice to have this in hand for study of carbon chains in general. So as a summary, hot Corino studies will require high sensitivity, sub-arc-second angular resolution, which is already attainable actually. They are mostly well suited for ALMA and JVLA, of course, not only, but mostly. On the other hand, there are not so compact objects like prestellar cores and WCCCs, which are rich in carbon chains, and that would require a shift towards low frequency observations, wide spectral coverage and resolution, and basically arc-second angular resolution or so. And some interferometer like NOEMA would be well suited for that. The study of a large family of organic molecules, which is that of the carbon chains. It is a relatively unexplored area, and it relies on the low frequency end of the millimeter range. So I know it was mentioned before, but in an ideal world, one would ask to reconsider or leave the discussion of considering development of these receivers for NOEMA. And I will end here, and thank you for your attention.
You, Anna.
Okay.
There's a question by Anaël.
Yes, thank you. Super nice talk.
Hi.
Hi. Very nice results. I'm really looking forward to see more of the first results out. So regarding your argument to go to lower frequencies, I fully back this up. I think at least for the dust, it's obvious when you want to go to this very high density, we have to go to low frequencies. I mean, people doing this have been forgetting this recently and realized and discovered again optical depth. So, but for the line, so you want to go get the transitions of the hot Corino type molecules, methanol, and all the things beyond. At low frequencies, but then I expect that these transitions would have lower excitation conditions, so we would actually not trace the very warm gas, or am I mistaken? I mean, basically would not trace the same gas as with the Ben 6 methanol and so on transitions, no, if you go to 30 gigahertz.
You're talking about hot Corino, so in this case icons, right?
Yeah.
I'm not sure. I believe there's a mix of transitions at all wavelengths, actually, because they are complex molecules. Maybe as a general rule, yes, but for example, one can even go to the centimeter and observe methanol and be tracing the hot Corino, and that has already happened. So it's not like a general rule, I would say. If anybody wants to complete, but for icons, that is my feeling.
But so why
jump in? Sorry, Cecilia. May I jump in on this? Because there is in principle, you're right, Anel, but the point is that in hot Corino, practically the region is determined by the front of the evaporation of the sublimation of the mantles from the temperature. That is practically sort of a jump function. So in this sense, even is not lower frequency transition do not necessarily trace a different gas, just because there isn't a different gas beyond or in front of the hot Corino.
Okay, so you still so what you're saying is that yes, these transitions still are at upper level, well, typical excitation temperatures that are beyond the 100K.
Say it again, please.
that there are still quite high excitation temperatures, even if they are lower frequency transitions. Basically, this is what you are saying.
Yes, they trace still the high, the warm gas, just because in the cold gas the molecule is not present. So there is so is instead of being a problem of excitation or radiative transfer, is chemistry that is playing the role to clean out the things. Of course, this is the ideal world in the practice. Obviously, it's not totally completely and so on, but in the ideal world is like this.
Okay, but then why do you need less angular resolution? I don't understand, because for me, the idea that you don't need the subarc second means that the emission is more extended, so you are probing less warm gas. I don't.
Because there are different objects. Yeah, maybe I don't know if I was clear enough. Like for hot Corinos, yeah, we do need the angular resolution. For the more extended prestellar and WCCC objects, we don't.
Okay.
So it's different kinds of objects and science cases. Yeah.
Okay. Do you really believe hot Corinos and WCC are different objects? We had this discussion at the workshop, PCMI workshop, actually last week, and I think now we are finding objects that have both, no?
Yeah, the hybrid objects. Yeah. If it's not true that the pure WCCC exists, it's making it very difficult for us to prove it wrong. Because there are 2 or 3 objects which don't show any signs of not even methanol, even at the centimeter wavelengths. So like there's no dust obscuring the thing. So something is chemically different. Of course, there are hybrid objects. There's everything in between the pure hot Corino and WCCC. And I would dare say that the 2 extremes are not the dominant ones, maybe. But there's statistics missing, as I was mentioning. Characterizing protostars chemically is a very painful and time-consuming job, and we are far from getting a statistical picture.
Okay, that's fine. I know the problem.
Yeah. Thanks, Ana.
May I ask why? Because I heard also yesterday this question, and I was surprised to hear that. Why you ask the question? No, I'm serious.
Question about which
from
question?
From our point of view, Anna already answered, but I was curious why you have the question.
Which question?
We can probably discuss this in the roundtable.
Okay, sure, of course.
Because we are on a tight schedule, unfortunately.
Sure.
So thanks, Anna, again for your nice talk.